transmit 5 species of malaria parasites belonging to the Plasmodium species to human. And they can be a huge burden depending on where you are. It's a global problem, and it makes so many people sick. 229 sick per year in the year 2019. We've not gotten the 2020 estimate. We all know what happened in 2020, but the latest is 2019, 220 million, and 409 people died of malaria that year. So when we look at this image, that is a very popular image from Professor Miller, showing us how mosquito has cast a shadow on the whole world, especially on the planet, the continent of Africa. We also can look at the incidence of malaria. Since 2002, the incidence has gradually reduced. We've been taking note and doing steps to reduce it. But still, we have some issues because we kind of stopped in 2016 and the incidence is climbing up again. I will tell you that this is an estimate. The true number is maybe unknown. This is because I've had malaria several times, and several times I did not even go to the hospital. So these are the reported cases. The good thing is the number of deaths due to malaria is gradually coming down. It is coming down, but it's still significant. And as I said, malaria is a problem that casts a shadow on the whole world. So it's good to have an historical perspective. Wherever you are in the whole world, except if you have been living in the Antarctica, malaria has been in that place before. It's even been said that it might have been one of the contributions that led to the fall of the Roman Empire. That is how amazing it is and how widespread it is. We can also go back and think about today. A lot of people in the Western world do not even know what it looks like, but we've been there in the past. And with the global climate change, there is a possibility that we could go back there, which means we need new ways of managing it. As I said, a lot of people in the Western countries and several other countries of the world, the advanced countries, do not even know what malaria feels like because it's been gone generations ago. But it's still there for people in sub-Saharan Africa, in Asia, to know what it feels like to have malaria. So I'm gonna take a moment to describe what malaria feels like. So it's a disease of the red cell of the blood. I have had it about 50 times in my life, and it comes in a weird, different way. So my earliest feeling is this: hallucination, nightmare, and then we get to high fever, chickens tail. So one recurrence dream for me, when I know the malaria pain is coming, is a dream where I see my head 50 times the size of my body, and then trying to struggle, trying to get through a door. And the weight of the head is counterbalance the weight of the body trying to get through. Think about that for a moment. Then, because of the chill, the lysis, rapid lysis of the blood cell, you have a lot of muscle pain, you have anemia, and it can go on for a while. And for younger kids, it can actually be very, very fatal because the high loss of red blood cell can cause a lot of complication. But one of the other complications is cerebral malaria. So where the parasite gets into the brain and it becomes a bit of a sticky glue that can block arteries, cause a lot of complication. And it is the most common cause of childhood death in Africa. It affects kids that are less than 5 years of age. I survived because I did not die by the age of 5. But it is not like it's fun. Each time you still get it, it still keeps you down all the time. So with all of this knowledge and all of these issues, how do we even keep this under control? What is helping us to control malaria? It is a multidisciplinary approach that is being worked on in different angles by different professionals to keep the area safe. So one of the easiest things I mentioned, mosquito is the greater transmitter. So if we can do vector control by doing residual spraying using insecticide treated bed nets, as you can see in this picture, we can reduce the transmission. Then these days we've been blessed with improved drugs. We've had some drugs in the past. And when you look at this graph of estimate, you can see that gradually, just a reflection of the other graph that I've shown you, there's been steady decrease in the number of deaths and the steady decrease in the amount of parasite that we've had or the amount of malaria. I will still reiterate, this is a conservative number. The true figure may not be completely known, but at least we have a reference. So the importance of insecticide-treated bed nets. This is one of the most cost-effective intervention in public health. And it has really, really reduced malaria deaths in the whole world. So it's quite cheap. And a lot of governments in the world, through sponsorship, are actually giving this bed net out to different parts of their community to reduce the scourge of malaria. The figure on this left side shows you by the year 2000, the distribution of bed nets in the most impacted region of the world, the sub-Saharan Africa. You can see that nowhere was using it. But then by 2012, some countries are close to 90-something% use of insecticide-treated bed nets. And so there is encouragement in the use, and that might have reflected the decrease in the amount of incidents and deaths due to malaria. The big challenge is that there are several socioeconomic and sociocultural aspects that will not allow this deployment to be effective. A lot of the area in which malaria is rampant are very poor countries. So you can have a question and ask yourself, I got bed net, I live close to a river. Which one is easier? I use the bed net to get some fishes and feed my family, or I just use it and look at it like that. So that's the sociocultural, socioeconomic impact that may make people use the bed nets that they are supposed to sleep under to look for means of feeding their family. There is also sociocultural issue about beliefs. Some cultures do not want to sleep under the bed net because they believe there are witches and wizards that can come in the night. And when they are separated or sleeping under the bed net, they are separated from their powers. So they do not want to be killed by remote control from the witches and the wizards. And that discourages the use of bed nets in some parts. But it's encouraging that we're moving, at least slowly, but we're moving. Then, as I also said, there is improvement in drug used for malaria. So one of the most effective drugs is artemisinin-based drug. It is from a Chinese woodworm plant, and it's been known for ages, even before Christ. And they know it like it abates fever from malaria. Remember, I told you, except if you live in the Antarctica, every part of the world, every continent have had malaria in the past. And so it was there in China in those days as well. And this was a drug that is used, a plant product that is used until a Chinese scientist by the name Suyoyo isolated the active anti-malaria component of Chinsu plant in 1972. That is a significant contribution to saving life, and she won a Nobel Prize for it in 2015. You can look at my talk so far. I've mentioned 3 Nobel Prizes. Malaria is that important. It gives a horrendous amount of work and a good chunk into the body of science. And it is very, very, very important. So artemisinin combination therapy is the drug of use in most parts of the world since 2000, the year 2000. It is a very effective drug. It acts very, very rapidly. And because it acts very rapidly, it takes down a number of parasites quickly, so the relief is fast as well. And it is the drug of choice in Africa and Southeast Asia. So this is the chemical structure of artemisinin. But because it acts rapidly and it's eliminated very fast from the body, there is the need to combine it with another drug. And that is why most of the time in Africa and Asia, you have artemisinin combination therapy. In this case, the drug that is mostly combined with it in Africa is lumefantrine. This is an anti-malaria that is not also as effective. It's not as effective as artemisinin, but it stays in the blood for a longer time. So when artemisinin is done, they take care of the few other parasites that is in the blood, and it is being a drug that is contributed to the reduction in malaria. With all of this knowledge, we can always ask ourselves a significant question. Why is it that half of the world still live in countries where transmission continues? Why do we still have so much pain and death because of malaria? The answer is very obvious. Bugs have survived ages, malaria parasites especially. And so we fought hard to get rid of them, and they are fighting back really strongly. And it is not only parasites, we also have the mosquitoes developing resistance to insecticide. So I'm showing you 2 different pictures around here. The first one is looking from the year 1995 to 2000. And please notice the red dots. Those are colors of susceptibility of insects to the insecticide treated bed net. The green ones between 1995 and 2000 are areas where they are sensitive. You look around Africa, especially in the malaria belt, you had some green, a lot, but less red all over. Now, in 2008, between 2008 and 2014, look around the belt, you see a lot more of the red dots. Those are areas where we're seeing resistance to insecticide treated bedding by mosquito. And that is a problem because we are trying for mosquito not to get to us. But now the treatment that keep them away from us, they figure out a way to just like, all right, that's not working on me. I'm still gonna find my way to you. And that's a problem for malaria control. So they have become less effective. Then there is also the coming of resistance to the drug that we use, resistance to artemisinin combination, and it's spreading in a lot of Southeast Asian countries. And that is a huge, huge challenge to malaria control because if our drug is not working again, then we have issues. We've had drugs in the past, several drugs that have become useless because the bugs are resistant to them. So in the case of artemisinin combination therapy, we've seen delayed clearance of malaria parasites. As I mentioned earlier, the advantage of artemisinin combination therapy is like it kills the parasite very fast and relief is fast. But now we're having delayed clearance and worse outcome. So with this slide, it brings us to a harsh reality. The public health challenges of today's malaria story is significant, but available tools are not adequate to make substantial impact in some parts of the world. And that is a true statement. So what do we do? The dream of ending the scourge of humanity is within reach, but it would demand our best collective efforts, which means we need to figure out new ways of dealing with our problem, which is malaria. So big question is this: what do we need? We so far have talked about what we've been doing, and we know a lot of what we've been doing is great, but the question still remains: how can we improve what we've been doing? We've talked about drugs. We've talked about vector control. We are not talking so much about diagnostic because we know how to figure it out. We've not talked so much about vaccine. It's not like we're not working on it, but it's been very, very, very challenging to get vaccine. So it is a saying that there's a problem. Mine is, which way can I contribute to solve the problem? And our own way of trying to solve this problem is doing what we know how to do, developing drugs. And our question is, several drugs have been developed and brought to the clinic for malaria, but several of them have gone down the road. What can we do that is different so that we will have a different outcome? And that comes from several ways of looking at it. First, we will look at the life cycle. Then I will look at my own personal experience, having had malaria several times, and each time is not better. Then I ask myself, vaccine is great, science is excellent, you can never say never. But if I have had malaria 50 times, and each time it's really, really, really kicking my butt so bad, how can a vaccine help me? will the vaccine be able to help me? As I said, you can never say never in science. So I have hope that science will figure it out. But what can I do right now that is better and faster to get us some relief? So our strategy is this. We will look at the life cycle and talk about all the different drugs and think about how to make it better. So, problem with all the drugs, all of them treat a specific stage of it. This is the malaria life cycle. Mosquito will bite and inject sporozoites, which goes into our liver, and slowly they divide. And the liver releases this eventually into the bloodstream. When they are released into the bloodstream, that is when we feel the pain of malaria, the symptoms coming. And it is very, very severe. And as this stage, which is called the asexual stage, goes on, we also have a different stage going on at the same time, which we call the sexual stages, in which there is a male malaria parasite and a female malaria parasite circulating. Because of how we think human, we want to solve a problem. And what is the problem here? We are getting sick. We are feeling chill. Kids are dying because of this asexual stage. So almost all the drugs that have been developed for malaria attack this asexual stage and give relief. They help us clear the parasites from the blood. But all of the drugs do not touch these sexual stages. And because they do not touch the sexual stages, the cycle is still continuing. There is one drug called primaquine. It is one of the few drugs that have an impact on the sexual stages. Artemisinin have some impact, but not as much as this primaquine. The problem with primaquine is that areas of West Africa or Sub-Saharan Africa where the issue of malaria is, this drug is toxic because of an enzyme that is in the system of most of these people living in that area. So it cannot be used so much, cannot be deployed. So the big challenge is this. We clear the parasites in the blood, but also in the blood, we have stages that is not touched by the drug, and it is continuously going. That is the stage that mosquito will pick and will infect mosquito. The big challenge is also this. That stage can be in the blood, even if you do not have the parasite or you do not have the symptoms, you are still transmitting it to mosquito. It can be up to 4 weeks after you've cleared your symptoms. And in some areas, you have people that actually have low level of parasites and they walk around, they are not sick, but they have this asexual stage going on in them. And so they are walking around as a stage for which mosquito can easily pick parasite from you. And so people are transmitting it all the time, which makes it being around all the time. Think about that. The parasite is very smart because you cleared it, you don't have symptoms, but you're still doing a thing underneath to keep the species perpetuated forever. And so our contribution is thinking about it. We will not develop a drug that will touch the sexual stages. The sexual stages. We do not want to develop a drug that will relieve you of your malaria. There are several of those ones. We want to develop a drug that will prevent you from allowing the sexual stage to be transmitted to mosquito. And I mentioned earlier that this parasite is being transmitted in the blood for up to 4 weeks, even after your symptom is gone. So if we want to be clear, we know that we need to develop a drug that is not toxic, that is easier for you to just put in your mouth, maybe like a gummy bear, and that will be around for a long time so that it will reduce your chances of transmitting parasite to mosquito. It will also have a use because when we say, all right, we are going to develop a drug that will not treat your disease and will not allow you to transmit it to your colleague, you will sit down and regulator will ask you, that is dumb. We got that. That is silly. How will you do that? What do you want to do?
I'm not sure I understand.
Oh, sorry for my phone. So, like, why will you do that? Why will you want to have someone take a drug that will not help them? It's really, really unethical. And that's true. Why should you take a drug that will not help you, but will help your neighbor? So, to encourage you to say you have to take this drug for every one of us, we must make it be very safe. And we must make it to be like you really want to take it. It should be tasty, right? You should not have to get a painful injection for you to want to take it. And we should make it like it's worth your time because we don't want it to become resistant. And resistance is important because we mentioned that a lot of drugs has been developed to malaria, and a lot of them have become resistant. Even our beautiful ACT is having resistance issue. So, looking at a stage in malaria parasite that will have less resistance is very, very important. So, for us to make this happen, we have to also make sure that it will do a lot of tests to make sure it works. And so it brings us to our discussion today. How do we protect mosquito? We do not want mosquito to have malaria so that we don't get malaria from mosquito. This is the life cycle of mosquito. This is what they do. They drink broth from us, and in this life cycle, you can see the different stages of the malaria parasite in human. We go through different stages. But the easiest one to think of is this. Malaria parasite will change shape and configuration when it gets from human inside mosquito. It is like we go through different weather. It's summer, we need bikini, we need to get to the beach. It's nice. It is really hot. We do not want to have any layers of clothes. But it is winter. Oh my God, the temperature is too cold. You need to get padded up. And so there are signals in mosquito to tell them you're here now. You are in the mosquito. And one of those signals is an enzyme called calcium-dependent protein kinase 4. It is an essential enzyme that tells the parasite you are now inside the mosquito. Now you need to behave differently. You are now inside the mosquito. It is the stage for sexual, it's the sexual stage of your life. And as I said in the beginning, there is the male and the female parasite. So once you get the parasite gets into the mosquito, the male separate out and the female separate out. And they have to have sexual mating inside the mosquito for the parasite to develop. It's just a case of boys and girls. Dating site is what the mosquito provides for them to continue. This enzyme is very, very essential for that process. And if you don't experiment to genetically knock this enzyme out, sexual stage is done. And I'll show you what it does in the next slide. So, boys will always be boys. That is the nature of life. And the process that I'm going to show you is actually the process that Laveran discovered that opened her eyes to know that malaria or bad air is not due to bad air, but due to a parasite. So when the parasite gets into the blood, the mosquito, within 10 minutes of getting into the mosquito, there are signals that go out and say you are in the mosquito. So the male mature and boys bring out what they do best. Now look at the slide. You can see the male within 10 minutes bring out sperm-like system. Each male has about 8 of them, and they are looking around for the best, prettiest girl in town. We'll do that again. You can see the flagella-like tentacle. Those are sperm-like system that the male parasite bring out to fertilize the female parasite. And once that fertilization occurs, the life cycle proceeds. Nature has it that this must happen within 10 to 30 minutes of taking the blood meal from human. That means mosquito take blood meal within 10 to 30 minutes. This process must happen. If it does not happen within that period, it never happens. So the enzyme calcium-dependent protein kinase 4 regulates this process. So what we do is just develop a drug. We call it molecular condom, which prevents the boys from getting to the girls. And if we can prevent the boys from getting to the girls, we block malaria from getting to mosquitoes. So we are all about protecting the mosquito from getting pregnant with malaria parasites. Isn't that cool? So, big question, this is a kinase. And if we remember biochemistry, kinases are unique. They are kind of enzymes that phosphorylate other molecules for them to continue the signal transduction. Kinases are they all need ATP to do their work of phosphorylation. ATP is a universal molecule energy substance. So ATP is the same in plants, animal, insect, parasite. So kinases almost always have a very, very conserved binding site where ATP binds. This is the structure of ATP. It must make a conserved interaction with the end region of the kinase, and then it can be phosphorylated. When you look at all of the area, there is this residue called the gatekeeper residue that does not do anything with anybody. It just stays there. There's no interaction with ATP. And the amazing thing about that residue is that for all time, most times it is always a larger residue in human or mammalian kinases. So large residues are phenylalanine, methionine, leucine, threonine, and so they are always big. But for our enzyme, we have a gift from nature. I'm showing you the alignment of different epicomplexan parasites, for which malaria parasite is one of them. When we align the active sites where it binds for many of these different parasites, we notice glycine in Toxoplasma gondii, Cryptosporidium parvum, and malaria parasite, we have the serine residue. So when we compare the sizes of alanine, glycine, and serine to all of these, it's a smaller residue. And that is the key. As I said, look around, most of these are really conserved, even with human. But there are just those little differences, and that is enough for us to take advantage of the situation, for us to design a system where we can think of building in selectivity. That means what will only kill the parasite, but not affect human. Everybody's taken drugs in the past that has given them side effects. If we do not want side effects, we should have drugs that will only affect what we want to kill, which is a parasite, and not us. And that is a very important aspect. So our contribution, we developed a series of compounds called pump kinase inhibitors. We developed them against other protection like Toxoplasma gondii and Cryptosporidium parvum, which cause some other diseases. But they are also useful against malaria. We call them pump because of their chemical structure. I showed you ATP. ATP has this conserved region, this chemical structure. But the bump is this region, which is a huge aromatic group. And I will show you how it works in the next slide. So this is a small cartoon of the molecular basis of how these compounds actually work. I mentioned earlier that the gatekeeper residue does not do anything. ATP will have three conserved or some conserved interaction with the kinase. But the gatekeeper region is always large residue in mammalian parasite, mammalian kinases. But for Plasmodium falciparum CDPK, it's a small residue. So this bump can fit into that area. Because it can fit into that pocket, it will inhibit the activity of this enzyme and mess it up. So we can develop that as a drug. The only challenge is this. If you think this, for instance, is a mammalian enzyme, this is what happens. There is a large residue there, and the space is reduced. So this large residue pushes the compound out, and it cannot make the hydrogen bonding that it needs to inhibit this enzyme. So mammalian enzymes, most of the time, are not inhibited by this enzyme. So we will not have side effects. And it goes back to my discussion earlier that we want to make this drug because it's not gonna treat your malaria. You still want to take it because it's not gonna hurt you. This is the building that it will not hurt you. We have used this knowledge in several ways. to develop different compounds, because it's always theoretically easy to think about compounds. Yeah, this will work to kill the parasite, and that's it. But no, it doesn't always work like that. This may work here to kill it in the test tube, but then you have to take it. But there is issue when you take it. And so we have to go through different stages of changes and working around to make it perfect drug. So you're looking at all of these different molecules. They look similar, but for really little changes. And this is how they behave. You can say that this is a short packaging region, and then there is the IC50 against T-gun. It's small, but then you get to 95. It's just like, oh, it did a little change and it improves it significantly. It's still the same compound. Everything is the same except for that added methyl group. But then you had another methyl group and boom, it throws it out of whack. This is using our knowledge of the compound and then the crystal structure of the molecule, of the protein, to work around and make the compound better for more potency, and also think about for pharmacokinetic improvements. So this is what happened in that area. We had a methyl group, and then it made an additional hydrogen bond with another residue, so which makes it tighter and inhibit the enzyme better. And so it makes it much potent agent. And using this, we've made several compounds using different combinations of bumped or side chain on the R2 group. Over 800 molecules have been made. And we have used this to improve both the potency on the enzyme and then potency in killing the parasite, then also reduce toxicity to human or others. Our first breakthrough compound is called BKI1. It is when we look for drug that we want to take orally and it is useful. It is not toxic. It's really very good compound. And you can look at the compound. The big problem is it is chewed up easily by metabolic enzyme in our body. So this region is opened up and then it messes up the compound by enzymes that we have in our body to protect us. So to protect this group, we added a pyridine group, a methyl group, to make it compound 1294. So this protection improved the amount of the compound in the blood by 8-fold. You remember, malaria parasite is in the blood. And so for us to protect against mosquito, it has to be in the blood, because human will take the blood, will take the compound, and it has to be in their blood every time when mosquito take blood meal for it to be useful. So this compound helped, and it was a good improvement to the previous compound. You notice, as I said, it's just a tiny change that made that huge difference. Then for that compound, it's really very good on the enzyme with that little change. And it does prevent the process that we want to prevent, which is the fertilization of the female gametophyte by the male. So it's a very good birth control for malaria parasites. We have done a proof of concept in both mosquito and in mice, and it reduces everything. It's worked really, really, really well. against other human kinases, it does not touch except for one, which is PKD3. That's another story for another day. The only problem is that it has effect on another enzyme called HOG. This enzyme can cause sudden death because it affects human heart rhythm. So we cannot use this drug for human because we do not want to cause sudden death. These are things that pop up unknowingly in drug development. It has every good property for a good drug because it's so cheap, but it's still unuseful. We use it as a proof of concept, and we can see that if you have 3 micromolar of this compound in mice, it will perfectly not make mosquito pick up malaria parasite from you. We've done this in mice and it's worked excellently. So I'm going to give a recap of what we've been discussing so far. We want to block transmission from us to mosquito. And we've had a proof of concept compound, which worked really well. We have injected the compound in mice, and in mice infected with the parasite. This is a stage in which we inject it, and we can see that it will not allow mosquito to pick malaria parasite from the mice. These are 2 images. This is untreated. This is treated mice. You can see those dots are malaria parasites that are in those mosquitoes that bite the untreated mice. While in treated mice, you have no parasites. And when you have no parasite in the mosquito, you have no parasite going to human. This is an effective and wonderful proof of concept that our hypothesis is just not hypothesis. It can be applied to nature. So our challenge is we need this to be in the blood for a long time. But even with the improvement we made for 1294, it still cannot be in the blood for a long time. So we've been making other improvements, and this is a newer compound that we've made. This compound will be in the blood for a long time. And a little change in the structure will allow the compound to be taken up by the liver and then tossed back into the blood so that it's going up and down all the time in the blood for several days. This compound, we've given it in a single dose to calves and horses, and it can last there for about 7 days. When we think about that in human, it can be 10 days protection. The big challenge is still this. That's not enough. We still need to do better. And it's a very, very potent drug. So our question is, how do we even improve this to be longer? We have done tests to show that it will protect, even with human blood and everything, against transmission. So what do? We are trying every possible ways to find a way to apply this drug. One of the early questions is like, if we have to do this, can we just keep the drug to mosquito by providing sugar water? And we did that experiment. We found out like, well, maybe 1294 is not a good one because it is horrible. So it's so bad that mosquito will not even want to take it. We mixed the compound with honey and gave it to mice. They will not take it. So we had a horrible outcome. But even as bad as it is, you can still see like it reduced it a little bit. The big challenge is this. The process that we are inhibiting must happen within 10 minutes of the blood meal by mosquito. What are the chances that the mosquito bites someone and goes to drink water in 10 minutes? That is not really visible. There is a question of we should put the drug on the wall. What are the chances that the mosquito would go to the wall and lay in the wall within 10 minutes and get the blood into its system in 10 minutes? It still means like we need to get this through human. So the goal is to find a way to develop this in several ways such that it can be used by human. So I'm going to give a quick summary now of what we've been discussing so far. Transmission blocking is very essential to malaria eradication, as we've seen with insecticide-treated bed nets. And an additional two will be to do the compound that we've developed that can be used routinely such that it's in the blood all the time. And each time mosquito come in, it will eradicate, it will not allow malaria to be transmitted to mosquito. There are questions of how to apply this drug and the ethical challenges of why do you have to take it. We think it may be okay to combine it with another drug, artemisinin combination therapy, and or other drug. So the advantage of that is it will protect the gain that we find, because if someone take that drug, it will not allow them, even if they have resistant parasites, to transmit it to the next person. But as it is now, we can say that this experimental drug do work as we intended it to be. So what are the things that we're thinking of? We want to really figure out how to do the blood level and do the modeling and feasibility study of what this can look like in real life. We've done few of those ones, and the other big question is how do we deliver this? As I said, human must take the drug. If humans take the drug, how do we give it to them? So there is a question of we can do it as a single drug, but that ethical question still remains. Why do you want to take a drug that will not treat your malaria, and just because you want to be nice to your neighbor? You should think about your neighbor as being helping yourself, if you think about it, because if your neighbors do not get malaria, it will not come back to you. So this is a question that people in sub-Saharan Africa, like, there is no problem, because in a household with 8 bedrooms, there could be 4 families. So if one family gets it, every one of us will get it for the rest of the year, because as one is done, the other one is picking it up and it's circulating. But it's still a challenge, a question that we need to answer, because it is a valid question. So if we combine it with artemisinin combination therapy, it will be, we think, maybe more acceptable, because at least you're going to treat your malaria with artemisinin, and this will prevent you from transmitting resistant strain or keeping the resistant strain around. So it will overcome our ethical challenge, but it will become more expensive, because we have to see the challenges that come with combining 2 drugs in terms of drug-drug interaction and everything. But we should also know that there is an advantage, because it can help us protect artemisinin combination therapy. There are other things that we're thinking of in the future, but I think for today we can keep the discussion at this point, and we will continue in future how to move forward. So I will like to end this talk by acknowledging a lot of people. This is just a little slide to show few people. It's a work that is been going on for years and had so many people from different aspects coming together to solve the big malaria question. And with that, thank you for your attention. And if you have any question, please let me know.
All right. Thank you very much, Dr. Ojo, for that very informative talk about malaria. So we do have some questions, and our first one is about the map you showed us at the very beginning of the presentation. And the question is, do you know why malaria has been historically absent from Central Asia when all of the surrounding areas had cases?
Central Asia has had it in its own long time. The only area that did not have, never had malaria is the Antarctica region because it's really too cold here. It's always very, very cold. And temperature affects mosquitoes' efficiency in transmitting malaria. That's the basic reason why they have not. But over time, we had some areas that are warm, so malaria grows here, but they get cooler. And also there is also the question of infrastructural development. So areas that still have malaria are areas that do not have good infrastructural development. But it's very, very important, only the Antarctica region, which is always very cold, is the only area that have never had the scourge of malaria. Every other part, every other continent have had it. Does that answer your question?
Yeah, that makes sense. Thank you.
So our next question would be, does the parasite that causes malaria in humans have no harmful effects on its host mosquito?
That's a very good question. We believe it will have some effect on the mosquito as well because it's using some of the natural resources. And but it's not as easy to say, yeah, I got horrible fever today. We can do that in mosquito, but I believe it will have some effect on mosquito, especially when you think about length of the life of mosquito infected compared to uninfected mosquito.
So our next question is, has the COVID-19 pandemic taken resources away from battling malaria? And if it has, do you think that it'll continue to do so in the future?
Very, very important question, I will tell you. That is a good question. It's very, very sad. I would not be able to answer the question as confidently as I can say, but what the big problem is, most area, especially in Africa, sub-Saharan Africa, where the epidemic is high, the budget for malaria is not always huge anyway. And so there is a real good possibility that attention to COVID will have taken away some of the resources. But still, reality is also that these are not countries that are really so much invested, at least until recently, or affected until recently with the COVID scourge. So there may be some impact, but it is not still like very clear. Theoretically, it should be like significant, but yeah, the data are not completely in. To answer the question as confidently as I would have loved to. Is that helpful?
Alrighty, so our next question is what makes malaria so unique such that an effective vaccine cannot be developed?
Another wonderful question. That's why I love this group. Malaria, the parasite, is very, very smart. Let's keep it like that. When the parasite gets in, there are several ways in which it can present itself that make the body not recognize it all the time. It's also that our body also cannot mount the best amount of responses to it that is long lasting. So each time it comes in a bit of a different way, we fail to really respond to it like we should, because it may be a little different this time around. And then we do not keep enough memory cells or memories response, antibody response to deal with it. That is just the most simplified way that I can say I want to explain it. And that is one of the challenges of vaccine development. I've had it 50 times, as I said, repeatedly. And I've been exposed to it several times. Vaccine will be possible, but don't quote me. You can get all the different strains that is out there and put them in that vaccine. That will help. The beauty of sciences is this: we keep learning on how to get better with each failure. And we've had huge amount of failure with malaria. And with advancing technology, I believe we will figure out which part of our immune response that we can re-engineer or train with little help to make us be better in dealing with malaria. But for now, we have not so developed way due to the parasite and due to ourselves of dealing with it. I hope that helps.
So our next question is, does genetic engineering and sterilization of mosquitoes give a way to control the mosquito population and slow malaria spread?
That is a political question. All right, so I have a little bit of a bias to genetically engineering mosquito. So I will say that conflict of interest, because I believe in drug and also based on my own life experience. Engineering mosquito to stop transmitting parasites like malaria theoretically is visible and can work. We can never say never to science. But I have a few concerns about that. One, what happened to the ecosystem? What bad thing can we say come out when we engineer it not to be able to transmit malaria? Can it just result in transmitting something worse than malaria? Or how visible is it that we can repopulate the environment with these genetically modified mosquitoes? We've had a lot of amazingly stupid ideas in dealing with malaria using control of mosquitoes. the Gates Foundation thought about, all right, let's just get the laser, shoot out mosquitoes from all of these areas. Let's genetically engineer mosquitoes so that they stop transmitting malaria. First, shooting out mosquito will cause famine because I don't know, except if the laser can figure out a way to differentiate female Anopheles mosquito from the male. And if they kill all the female, how do we get the male so that they can pollinate our plants so that we won't have famine and food shortage? This. Or we genetically modify the mosquito and think they will repopulate the environment. That's been done, but it did not come out because there will be some fitness disadvantages. So my answer is I am biased. I hope that did not confuse you too much.
Okay, I think one of the other questions we had was, could anti-malarials be combined with sterilization and similar techniques for curbing the mosquito population without causing resistance?
I do not understand your question very well, sorry. Can you repeat the question, please?
Yeah, of course. So could anti-malarials be combined with sterilization and similar techniques for curbing the mosquito population without causing resistance in the populations?
How do we deliver it to the mosquito, the anti-malaria? That's one question. Then we want to be sensitive to the environment, want to be sensitive to the ecosystem. And that's why I said I have a bias with engineering or messing up with mosquito. There is a drug called ivermectin that's been proposed to be used for controlling malaria. The problem with that drug is it kills mosquito. It can reduce the malaria incidence and help us in some controls. But my big question is, when we kill the mosquito, are we not causing a bigger problem? Because if we do not have mosquito, we reduce our chance of saying, okay, we need plant to be pollinated or we need food. It's a lot of problem already in several parts of Africa where this is endemic. There's food shortages, and if we kill more mosquito or do things that will affect mosquito, we may increase the problem. Whatever we can do, knowledge is continuous. There is always that open room that someone will figure out something to bring that idea of combining anti-malaria, as long as it does not kill mosquito. My deal is to protect mosquito, and you can see it in my talk. We want to protect mosquito, keep them alive as much as possible, which is one of the reasons for our drug development. The drug will not do anything to the mosquito, but it will protect them because we do need mosquito. There is a possibility that someone will figure it out. That is the beauty of science. But as I say, figure it out without killing mosquito or harming mosquito. The technology is not there yet, but it will be there, possibly soon.
All right. So our next question, I think we touched on this a bit earlier, but why do you think that modern day malaria research is underfunded, even though it affects so many people?
Yes. That is a very, very, very important question. And it touches different areas of politics and human care to other humans. Then also, it also touches knowledge in areas where is important. So first, the countries that are mostly affected by malaria are poor. So they look out to other advanced countries to help. It is not the problem of America. So whatever we can give to help in managing malaria is just out of our goodwill. That is one issue. There is also the issue of companies that can make drugs. It costs millions and billions of dollars to develop a drug. But if you develop it and you know, like at the end, you have to give it out for free, why do you want to invest in that? You have to cater to your shareholders. That is another aspect of it. One other important aspect of it is people want results for us to even put more into it. There's been progress, but it's, as I showed in the graph, it seems to have been stalled because the bugs are fighting back. So if it is not that rapid, why should we just continuously put money there when we can't see? It's just a human nature. Then this is a bit of a political issue. People are very, very dedicated into solving this problem so much. They invest a lot of it, but most of those people that are doing the best amount of work on the malaria research do not and have not even had malaria once. They do not live in the belt. I brought up a question of ethical issue with the drug we're developing. My thought growing up in Nigeria is, this is what we need. But then presenting it to help they say, no, you cannot because this is ethical issue. For someone in Africa, oh, this is great because as long as you don't get it, I know I can't get it because we live in the same house. So why will you want to fund an idea that you don't think makes sense? That is also one of the things. So a lot of people doing the work, a lot of the funders are really, really do not understand the complete problem. Malaria is a problem that needs different angles to solve it. You will need different cuts to have impact. And each cut will help if you allow the cut to happen. One other aspect in the same line, because the countries that are affected are poor, scientists from those areas are always not at the head of every discussion. If we can help to change some of those cultures, it will help for someone to come out and say, this is a problem, we can explain it. One of the reasons why I feel like I love talking to young students about this is I can say something as someone that has had it before and someone that is working on it, so that at least what I say may touch someone that can talk to someone, to help to focus us on the problem and help a bit more of the funding. I hope that helps. It's a very long answer.
So our next question is, considering the recent proliferation of invasive species of mosquitoes, are mosquitoes from the Aedes genus more infectious or dangerous than other genuses?
That I may not be able to answer you correctly. Aedes they are not even as effective as the Anopheles species. And even within the Anopheles species, you still need some more effective one. Anopheles candense is the most effective one. They will transmit it most efficiently. So changes and in the mosquito, I cannot completely say because I am not studying specific mosquito, but we still know like impact of climate change can affect different organisms and different species that they behave a bit differently from what we're used to. And that is my takeaway. There is a possibility that changes can affect Aedes to become more efficient. We know Aedes are very efficient in transmitting yellow fever. Yeah.
I believe our next question is, have any malaria strains developed resistance or increased their infectivity among people with sickle cell disease?
Hmm. Sickle cell is a disease that is a response to the malaria scourge. And it's just trying to protect the body. Depending on where they are, depending on the strain of or the species of Plasmodium, it can be a problem. But they are better protected, a bit better protected, a bit more protected than every one of us. Whatever the case may be, it's better to have malaria than to have sickle cell.
Alrighty, so our next question is about another preventative measure. So do you think there's a potential for a bug spray as a preventative measure by preventing the mosquito from even biting the human in the first place?
Yes, that is being used, and that is one of the most effective system. But you also have to think about it. I've used in the past, like used this insecticide called Rage. We have new knowledge of the impact of this on human. But yes, if we can find some better ones that are less toxic on the long run to human, they work really well. Bug spray are great.
Thank you for that answer. So the next question is, let's say that at the active site, the residue is glycine as opposed to threonine in the parasite. Could an effective drug still be designed given that human cells have methionine residues at the location? Or is there something specific about threonine that was significant to the project?
Can I have you rephrase that question again, please?
Yes. Let's say that at the active site, the residue is glycine as opposed to threonine in the parasite. Could an effective drug still be designed given that human cells have methionine residues at the location, or is there something specific about threonine that was significant to the project?
No, the basic is just looking at the size of that residue. The size of the residue is very, very important in the first place. So there's nothing, human also have threonine. About 20% of our kinases have threonine gatekeeper. But that's about the smallest, if I'm correct, that is in human. So if it is glycine or serine, it can give us a chance of inhibiting only the parasite. And that's the significance there. The size of the gatekeeper residue is very, very, very important. As I said, about 20% of human or mammalian enzyme are threonine. So everything glycine, alanine, serine, that is smaller than threonine, is good if they are in the parasite. That is the key there. That is the most important key. We've done studies to look at what are the important residues in the active site that can give us that selectivity for just the enzyme. And the most important property is that gatekeeper residue, the size of it. If it is small, if it is glycine, which is the smallest, it's very good. If it is alanine, which is the next small, very good. Serine is also small. But when you have threonine there, it affects the parasite just like it will affect the mammalian enzyme. And we do not want that. Some level is okay, but we'll have to look at the enzymes that will affect in that way, that they are not very essential. We can still develop a drug against that threonine residue if it is in the parasite, but we just want to make sure that other mammalian enzymes that have threonine are not very, very important for us to have side effects. That is in a way for us to kill parasite. But when it is cancer, the same applies. A lot of the cancer drugs actually attack the threonine gatekeeper residue, like liver. Those are very effective cancer drugs, so that they attack the glycine residue, the threonine residue at the active site and kill off the enzyme that feed the cancer cell. So my explanation is, as long as it's smaller than threonine for the parasite, it's okay. But that gatekeeper residue is very, very important for this particular drug development program. I hope that answers your question.
Yeah, thank you for your explanation. So we actually have a bit more questions. So the next one would be, is the only feasible method of delivery in a cocktail with other malaria treatments, or could the drug be placed in a commercial bombs, for example, or in water supply as an added ingredient?
Very, very great question. I've asked that question, but I get a lot of pushback. I have asked that question in the past because today we have iodine and stuff in our salts. For instance, iodine is a case that is because in most parts of West Africa we use salt in our food. And so if you have iodine in salt, it provides it to everybody. So if you have this drug in something like salt, it's something as well. Big deal for West Africa is water is also an issue. Supply of water is a bit sporadic, but it is something that can be done. It will just take a lot of study to make sure that delivery of this through water or through salt, for instance, will not cause some other problem. Using that, the big challenge is all this regulation that we have to make sure this is safe, and we have not studied it. But it's a thought that we've had, that having it in water or in a food component that everybody eats could be a way to deliver it to everybody and keep it in the blood constantly. So yeah, that's we've thought about that. We've just not been able to study it as much as we can. We would love to.
Yeah, thank you for your answer. So Our next question is there any hesitancy towards anti-malarial drugs, like people not believing the drugs work or believing that they could be dangerous?
Malaria has been around for a long time. And so people know it. People have used different types of drugs. Yes, there are hesitancy based on some religious belief. I did my laboratory medical school in Nigeria. And those days we just want to know how to be good in doing procedures like bleeding ourselves or taking blood smear, doing blood smear. And that day I got one of my colleagues and I got his blood sample and I smeared it and I checked it under the microscope and it was filled with malaria parasite. I freaked out, like, dude, you have a problem. What's going on with you? Are you okay? And I told him, this is your blood smear. It is full of parasite. And he told me, oh, well, they are normal flora. So it's nothing to, it's like, you need to treat your malaria. I said, I'll drink holy water. So that is an example of someone that will not take malaria drug, but his body is so used to it that it's not getting sick with higher level, but the challenge is he's transmitting it to others because of it being in his blood. A lot of people know about malaria. They treat it in different ways. Some have had issues with it. I have had issues with chloroquine, with side effect to chloroquine. So reasons for not taking the anti-malaria will be varied. Some religious, some experience, some economic issue. In the past as well, I've treated it with natural products. And so it is a wide field when it comes to reasons why people will not take anti-malaria. I hope that answers your question.
Thank you so much for your answer. So the next question is, what changes were added to make BKI more stable in blood? How do you make sure this increase in size doesn't affect the inhibition of CDK?
That's a very, very nice question as well. We have a system of going through the system through our checks to make sure things are working. So we start with thinking about what changes are we gonna make. For this particular one, we changed the piperidine group to have an alcohol group. And that actually made it in such a way that it brings it to this process called hepatic recirculation system, in which when you take a drug, it goes into your liver. The liver metabolizes it and then toss it out. In this case, because of that OH group, it goes into the liver. The liver metabolizes it and then send it back into the blood. So the level in the blood goes up and it goes back into the liver. It makes a bit of a changes, send it back into the blood as well. So it goes back and forth and it takes for a long time to finally eliminate it in the blood. So that is the basic change that we made. And when we made the change to make sure it worked, we first tested against the enzyme to make sure it still inhibits the enzyme. And it did. Then we will put it against the malaria parasite cell to make sure it kills the parasite cell. It did. Then we want to make sure it's not killing normal human cell. And so we will test it against normal human cells and see like, well, it's not killing them. So it's now okay for us to say, let's put it in animal to see whether they have their forelegs up or they're still standing. And in all of those cases, it passed. And then we tested it against the in vivo model in which we infect the mice with the parasite and see whether they are still alive after the drug and they can not transmit it to mosquito. So it's a chain of tests, but the basic thing is, yes, we modify it to make it go back and forth between the liver and the bloodstream, in which is different from the previous one, in which it goes through the liver and it's done. I hope that is that answers your question.
Thank you. And I believe this is our last question. So, what percentage of people would need to take an effective BKI inhibitor in order to significantly lower malaria spread? Are there any subpopulations overly sensitive to BKI drugs?
That is a very important question, I will tell you. We've not put this in human. That's the first thing. What I believe is this. If we achieve greater than 50% compliance, we will have a good impact on malaria transmission. We will prefer it to be 100% compliance, but malaria is such a system that is smart, but it is not perfect. It has its flaws. Instance, it is not every time that you are bitten by mosquito that you get malaria. It is not every time that a parasite that is infected with malaria parasite bites you that you will have malaria transmission. So because of a system that is not perfect, yet smart, every change to shake the system will have a very good impact. Mosquito. Someone asked the question, does the parasite have negative impact on the mosquito? My belief is that it does, because mosquito actually do not want to get malaria. So when they drink human blood, there will be about 1,000, let's say 10,000 malaria parasites, but they filter it out so much that only less than 100, in most cases 1 to 10 parasites eventually infect that mosquito. So if the amount of parasite is not overwhelming, the chance that the mosquito will be infected is less. Which brings us back to, if we have a compliance of a bit significant, we will have impact because the transmission is not perfect in any way. And when I said it's not perfect, that is even with the best vector Anopheles candiens. They protect themselves as well so that they don't have malaria parasite. So yes, we will prefer 100% compliance, but if we get above 50, it will have significant impact. And the more we reduce the reservoir, the closer we get to eradication. Is that all the question?
Yes, it does. And I believe that concludes their question. So, Dr. Ojo, on behalf of SSP, we wanted to thank you again for taking the time to give an insightful talk about malaria and answer all of our questions. And we really appreciate it. So thank you.
Thank you very much.
All right, let's give him a nice big round of applause. Thank you. Some are actually clapping and some are using the symbol. So all in all, thank you very much, Dr. Ojo. Like I had told you earlier, I really enjoy this presentation, and thank you so much for taking time to do this for us.
Thank you very much. I'll look forward to next year. It's always fun Because the questions are very, very, very intelligent and really good question, and that's really makes it worthwhile.
Well, thank you. This is a great group of participants who love to ask really good questions, so I'm glad that you enjoyed them.